Welcome to this webinar about the newest solutions of beta in the domain of electronics. More specifically, I am going to present you the major developments in version 23.0 with regard to our ECAD importer plugin. The newest developments concern a feature called trace mapping. So first I will introduce you to the concept of trace mapping for printed circuit boards, and then I will demonstrate how to use it in a live demo. First of all, let's repeat a general introduction to what the ECAD importer does. So the ECAD importer was introduced in ANSA as a plugin in version 21.1. With ECAD, we mean electronic CAD, which is used for design, fabrication, and simulation of printed circuit boards. And it's crucial for lossless information between designers, manufacturers, and engineers. It contains various types of information for geometry, electrical elements, topological, physical, materials, fabrication, and so forth. And the purpose of our importer is to automatically generate ANSA models from the ECAD files. The ECAD file format that is supported right now is the IPC 2581 revision B, which is an open source format. It's intelligent, and it's supported by a large industrial consortium and most ECAD vendors. So the main features of our importer is that it supports multiple levels of detail according to the needs of the user and to the solver. So it's solver agnostic. You can use it for multiple solvers, and you can have various levels of detail according to the faithful representation that you need of your geometry and physics. It is easy to customize through a GUI wizard, but you can also execute it in batch mode. You can edit many things in the PCB, like the stack up, the thickness, the layer, select layers, fuse layers, etc. And what is new in the 23 is that we have introduced a new level of detail in the ECAD importer. So in the previous versions, we had 4 levels of detail. Now there are 5. And the new level of detail is sits right in between the previous ones. So it is better, it has better accuracy than the homogeneous layers and homogeneous board of the previous versions, and it has less accuracy than the full 2D and full 3D metallization. So what it does is to do an approximate modeling of metallic traces. So the metallic geometry, the information about the metallic geometry is there, but it's more coarse, it's more approximate than in the full 2D metallization and the full 3D metallization. And it presents a customizable trade-off between accuracy and CPU RAM footprint. So here is a quick visual refresher of the 4 previous levels of detail and the new one, which is in the center, which is called trace mapping. So previously we had the homogeneous board, where the whole PCB was modeled as a homogeneous slab of material. You had level 2, which was called homogeneous layers, and every layer of the PCB had finite thickness and was represented also as a homogeneous slab of material. The level 3 now is the trace mapping, to which I will come right after this slide. Level 4 is the full 2D metallization, where the exact 2D geometry is present as 2D faces. So all the metallic layers are present as zero thickness faces, and the dielectric layers are present as finite thickness layers. And finally, level 5, full 3D metallization, is almost identical to level 4, but this time the metallic geometry can be meshed in 3D. So you have 3D metallic traces representing the exact geometry of the conductors of the PCB. Now, in trace mapping, we have something in between. So we have metallic features, but they are not represented exactly. And what I mean by this can be best represented, shown in the next picture, in the next slide, by showing you these 3 pictures. So, what we do in trace mapping is we do not mesh the PCB according to the exact boundaries of the metallic geometry. So the mesh does not conform to the metallization geometry. It can be arbitrary. But we do map the traces onto the mesh. And by this mapping, we mean that we know the exact geometry of the metallization, and we calculate the metal fraction of each element. So in each element, we know how much metal is contained in it. And the results are shown in the middle and right picture. So the exact mesh would look like the left picture, where the mesh conforms to the exact metallic boundaries of the PCB. And the trace mapping mesh looks like in the middle and right picture, where we have a mesh which does not adhere to the boundaries. It can flow freely across the board, but we know which elements have metal and how much metal they contain. So there are two options, both of them are available. First, we have the binary trace mapping. So an element can be either metallic or non-metallic according to whether it contains more than 50% or less than 50% metal. And we have the analog trace mapping, let's call it like that, where we compute the exact amount of metal in each element. So the fringe bar on the right shows us how much metal is available in each element. Blue means zero metal, red means 100% metal, and all the colors in between represent the range in between. So we have the exact amount of metallization. And this is the view of the whole PCB in binary PID view and in metal fraction view on the right. We see that in this case, we don't have a geometrical model, we have directly an FE model. So we create directly the mesh, and this mesh is a structured solid mesh. So it consists of hexas and pentas, which are extruded from a base mesh. And as you can see, for example, the vias can be either filled or they can be hollow, depending to their diameter. So this is a small snapshot of a cutoff of a trace map PCB. So why trace mapping? Trace mapping is very useful in structural and thermal simulation of PCBs. Many clients have requested it. It can be used, for example, for solder fatigue analysis, where you need some information about the metallization in order to calculate the behavior of the PCB under stress, but you don't need the exact form because it would be an overkill in terms of elements. And the same holds for heat conduction and conjugate heat transfer CFD simulations. Many users want this approximation. And in this approximation, you calculate approximate material properties for each element. So you have a mixture of metal and insulator, and you compute equivalent material properties for each element. So it is the best compromise between metallization modeling and computational footprint reduction. So you have information about metallization, but you can use less computational resources. So your solver runs faster. And the other important thing is that you can fine-tune your accuracy trade-off by increasing or decreasing the mesh size. So if you want more accuracy, you can just increase the mesh count. If you want less, you can decrease the mesh count. But the metallization information will be there. And the fact that we don't conform to the boundaries of the metallization allows for more uniform, higher quality meshes. So what is the workflow of our trace mapping feature? First of all, let me note that in version 23, the plugins have been reorganized. So from now on, you can access the ECAD Importer plugin from a new category called Electronics and Electromagnetics. So in this category, we have two plugins, the ECAD Importer and the Azeris plugin. So the steps are the following. First, you select the level of detail, then you select your IPC file, you preview the stackup, you import the 2D features, you create the profile, you select the components, you create the base mesh of the profile, and you map the traces. So these are the 8 steps that have to be done via our wizard. And let's go right now to the live demo to demonstrate it better. So now I have switched to ANSA. So I go to ECAD Importer, I turn on the plugin, and I am presented to the first page. So right now I click to the third option, which is trace mapping. And I see that the second box, vias, is not active because we can select which vias will be present and which not by using another feature later. So vias can be drilled or not according to their diameter, but this is going to be set at a later stage. And the components box is active. You can choose to import components. You can choose whether these components will have fins or not, and so forth. So let's go trace mapping. The next page, you select the IPC file. So let's select our IPC file. This is the same step as before. And here we have the stackup preview. It is the same as in the other steps. Let's say that we want to import, for example, the first top 3 layers of our PCB so that it's faster right now for the demonstration. We accept the stackup. We have imported the first 3 layers. We go to the next page. So here we have some different options than before. First of all, let me run it so that it runs in the background. So we don't have to set the resolution here because the resolution of the mesh is going to be set later, but we have an option to draw the boundary curves or not. The boundary curves are not an essential element of the model. We don't need them actually for the model, but they are an optional auxiliary entity, the curves, for the ease of the user. So when we show the curves, we can later see how accurate the trace mapping has been. And they are also useful in case we need to create a custom profile so that we can see the extent of the PCB. The second option, which is new, is the option of filling only some of the vias. So if you check this, then only some of the vias will be filled with metal and the rest will be opened, drilled, according to this diameter. So I have selected 1000 micrometers, so 1 millimeter. Only vias which have diameter larger than 1 millimeter will be drilled. All the rest will be filled with metal. And the rest of the options are the same. So import features without FiNet or paths without FiNet and ignore features out of PCB profile. To give you a quick reminder, this slide, you can see that the red features on the left are all the features without FiNet. So they are descriptive and they are also mechanical features. You can choose whether to want to import them or not. And on the right, you have just the paths and vias without FiNet, the red ones here. And in the next slide, you can see the yellow features. They are the features that lie outside of the profile, and obviously they are descriptive elements. You don't need them, so it's best to ignore them. Let's now go to the next stage. Let's create the PCB profile. Here you have exactly the same options as before. You can have the profile that's containing your IPC file, you can use a bounding box, or you can import custom curves. Here we have used the profile of the IPC file, and we can see that now the profile is not a thick volume, it is just a flat face. And the reason is that this flat face is going to be the base from which the rest of the mesh is going to be extruded. So we only need a flat face here as our profile is going to be used as the base of our mesh. So in the next stage, we have to select which components we want to import. And this page has been greatly improved since the last versions, but for now it's just available at this level of detail because the user might want to import some of the components, and it's important to have a dynamic and easy selection of components. So what is important right now is to see that the list of components is grouped according to packages. For example, the package 805 has all these components, all these capacitors, which we can expand. And we have the type of the package, the name, the number of pins, the area of each footprint, the thickness, the standoff, the mount type, and the layer where they lie on. What is also very important is that right now, only the footprints of the components are displayed at this stage, and we can dynamically highlight them. For example, if I turn on this highlighter, I have highlighted all the components of 805, or maybe we can have only these two components, and we can select multiple components at once. And we can also filter. For example, let's say I don't want components that have less than 30 pins. Then we can say, right click, remove from import, and they are automatically removed. And now we can see which are left. Okay, we have only these components, and we can also deselect some of them. For our purposes now, let's go and sort them according to pins. Let's deselect everything from import and select only the first one. When I select it, it appears here, the biggest one, and the 805. So when I select a package, they are all selected together, all its components. And for a package, I can edit its thickness. So here I can say 1.1, and all the thicknesses are edited here. But for the standoff, I have to do it individually, but I can do also a massive editing here. For example, if I edit the standoff of these three components, I can edit it together. Okay, so let's undo the editing here. Let's undo it manually and import the selected components. Okay. And let's go to the next stage. Now you see that because we chose to create pins, the footprints of the pins have been projected onto the face of the profile so that the shape will be preserved after meshing. So here we have the general meshing options that you have elsewhere. You can have a general mesh, a solid structural mesh, or a CFD mesh. And you can have various types of elements. Let's choose quad elements. Let's choose 500 microns, and let's create a base mesh. So this means that we will have a base mesh of 0.5 millimeters, which will respect the rest of the outline of the pins. And this mesh will be used in the last stage, where we will extrude this mesh in order to produce one layer of solid per PCB layer. So here you can see the mesh. It has respected the outline of the pins here. And we are ready for the last stage. So here is the stage of the trace mapping, where we have one basic option, which allows us to use binary properties per layer. So this is what I told you before, where each layer will have two PIDs, one PID for metallic elements and one PID for insulating elements or dielectric elements. And in any case, the metal fraction per element will be calculated. The advanced options concern the discretization which is going to be used in order to calculate the trace mapping, the metal fraction percentage. So here we have the discretization resolution. In the background, a Cartesian grid will be used in order to calculate the metal fraction. And this is the resolution of this Cartesian grid, which is invisible. It's not something that the user can see, but it affects the accuracy. And the larger this number, the less time it takes to do the trace mapping. The lower, the more time, but it increases the accuracy. So it's a trade-off between time and accuracy. But if you want to see how much error you do, you can preview the discretization error. And if you are not satisfied with it, you can change this number. And here you will get the mean discretization error in percentage. And right now you see that it's calculating this error, and we will have a fringe view of the discretization error on all the elements. Okay, so here you can see how much error we're making when calculating the metal fraction with this method per element. We have from 0% to 6%, but the mean error is 1.06%, so it's acceptable, we can use it. As you can see here, we have the error per element. And the other option is the bounds of this invisible grid. It's not very important for the user. Usually he can leave it at 1%, the expansion of the box. So the final stage is to produce the solid mesh. We press on map traces and create solid mesh. In order not to have to wait for it, I can show you the results here. So this is the finished result. Let me hide the curves for now. Let me have a PID view. So this is how the mesh would look like. Let me hide the components for now. And let me produce a cut through the solid mesh. Example like this. So this is the final type of the mesh. You can see that some vias that are larger than a certain diameter have been drilled. Other vias have remained filled. For example, I think this is such an example here. No, it's not. Anyway, there are filled vias and drilled vias. And finally, let me show you another thing. Here we can also show the percentage of the metallization, but you have to load a custom fringe bar, which is available as a script. So we go to the script manager. We load this script, draw metal, and now we have this metal fringe bar, which shows us the exact percentage per element. So here you can see. And if you want to have a view of the metallization accuracy, let me hide the solids for now and show you the curves. So here you can see how accurate the mesh follows and the metallization curves, and how accurate the metallization calculation has been. Finally, let me go to the previous view. We can have this metal percentage as a custom user attribute. So if I go here and I go to user metal fraction, you can see for each element how much metal from 0 to 1 is contained in this. And this number can be later on used for calculations by the user, by custom scripts, for example, for calculating equivalent materials, which will be a mixture of metal and insulator. This concludes the presentation of the new trace mapping feature of the ECAD importer. Thank you for watching.